right, today we're going to be talking a whole lot more about how these molecular orbitals are actually formed. Hopefully you were able to look at the balloon video that I sent you and the hybrid orbitals explained video, because in both of those videos, the balloon video, just because it uses balloons, which is something we're all familiar with, it is super helpful for us to be able to see in 3 dimensions how these bonds are actually taking place around the center atom. The hybrid orbitals explained, he uses some really great animations to enable us to see the same thing kind of down on the atomic level. There are 3 principal ways that a molecular orbital can be formed, and I kind of alluded to this in the first video, but I'm going to go into more detail today. So molecular orbitals can be formed when you have 2 atomic orbitals that overlap. An example of that is going to be in an H2 molecule where you have a hydrogen-hydrogen bond. If you recall, hydrogen only has 1 electron, and so therefore it doesn't have any electrons in any other orbitals that it is going to hybridize. The only orbitals that are going to be hybridized are the ones where the valence electrons are. And so because this only has 1 electron, it's not going to have any orbitals to hybridize. So these are going to be only atomic orbitals. The atomic orbitals of this hydrogen and the one in this hydrogen are going to overlap, and then they're going to form molecular orbitals so you can have a hydrogen molecule. You can also overlap 1 atomic orbital and 1 hybrid orbital. You can do that if you're going to form a carbon-hydrogen bond, as in the molecule CH4, which is methane. Okay, so your carbon has 4 valence electrons, and so it's got electrons in both the s and the p orbitals. And so when it does that, it's going to form 4 hybrid orbitals, and it's going to overlap with the atomic orbitals from the hydrogen, which again doesn't hybridize for the reasons that we already mentioned. It just has 1 valence electron. And so this is an example of the overlapping of an atomic and a hybrid orbital to form a molecular orbital. Finally, you can also overlap 2 different hybrid orbitals in order to make a molecular orbital. And an example of that would simply be a carbon-carbon bond. Since they have, again, valence electrons in both the s and the p, they're going to hybridize all of their outer orbitals, and then they will overlap their orbitals to make a molecular orbital with those hybrids. Okay. Now, 2 different kinds of bonds can be formed depending on what is overlapping. A sigma bond is a bond that is right in between the 2 nuclei, and so it's concentrated between the nuclei along the internuclear axis. He did that with his big main round balloons in that particular video. Okay, the pi bonds are made from overlapping p orbitals, and if you remember the structure of the p orbitals go both above and below. They have 2 different lobes to them, and so when they overlap, then you're going to have that bond that actually also goes above and below the internuclear axis. That's where the electron density is located. Okay. In order to make a single bond, that's always going to be just a sigma bond. If you're going to have a double bond, such as we've seen in oxygen molecules and nitrogen molecules from your first year course, you're going to have a sigma bond plus a pi bond, where you have 2 sets of p orbitals overlapping. And then if you have a triple bond, you're going to have a sigma bond plus 2 pi bonds, which is basically 4 p orbitals that are overlapping each other. All right. So this is how your multiple bonds are formed with these different types of bonds. Once again, I've got a table kind of put together down here, and we're going to go through, if I have what kind of hybrid orbitals, what kind of bonds can I form from them, and how do I know what kind of hybridization is going to be present there. If I have sp3 hybrid orbitals, and remember we said this was formed from 1 s and 3 different p orbitals. There are 3 different p orbitals along the x, along the y, and along the z. So if I hybridize all of those, mix them all together, I can form 4 sigma bonds. So what kind of examples can I come up with to show you what that would look like? Well, CH4 is one example of that. So if I have CH4, if you remember the dot structures, Lewis dot structures that we drew from your first year, the Lewis dot structure for CH4 looks like this. So it has taken all 4 of its electrons and it is sharing electrons with each one of the hydrogen atoms. And so it's got 4 single bonds around it. Another example of sp3 hybridization is in an ammonia molecule. With an ammonia molecule, it has 5 valence electrons, and so the dot structure looks like this. If I bond that to 3 hydrogen atoms, then I'm going to have a hydrogen here, a hydrogen here, and a hydrogen here. Since I had an sp3 hybrids, but the lone electron pair is stored in that 4th hybrid orbital, okay? H2O is another super common example of sp3 hybridization, and you've looked at the structure of an oxygen or of a water molecule for a long time already, I'm sure. We talked about it in biology. Water molecule is an oxygen singly bonded to 2 hydrogens, and it has 2 electron pairs left over. Okay, again, this is something that should look very, very familiar to you. So what do all these have in common? How can I look at these and say, oh, I know that that's sp3 hybridized? Well, I know it because each one of the central atoms has 4 things around it. 1, 2, 3, 4 hydrogen atoms. The nitrogen atom has 1, 2, 3 bonds plus a lone electron pair, total of 4 things around it. The oxygen atom has 2 hydrogen bonds, 2 lone electron pairs. Again, 4 things around it. So if you look at a central atom and you see 4 things around it, whether they be bonds, single bonds, or whether they be electron pairs, you can know that that particular atom has sp3 hybridized. All right, let's look at the next type of hybrid orbital. The next type of hybrid orbital is sp2, where it's taken taken its s and 2 of its p's and hybridized, but it's left 1 of its p orbitals out of the hybridization. If it's going to do that, then it's able to form 3 single bonds. It can form a pi bond because it's got those p orbitals left that it has not hybridized. So again, let's look at some examples here. O2 is probably the most simple example. And so again, if you remember, oxygen dot structure looks like this. It wants to have an octet of electrons around it so that it looks like the noble gas, so that it's stable. And so it's going to share both of these guys and form a double bond in here. So now it each has each one of the oxygens has an octet of electrons around it. But what's actually happened here? Well, the sp2 hybridization is responsible for 1 of these bonds, and then this lone electron pair, this lone electron pair are each in 1 of the other 2 hybridized. But the fact that it's got this other bond up here means that that has to be a pi bond, and it's the p orbitals that are overlapping to make that double bond. Okay, another example of this type of hybridization is C2H4. Okay, and so if I have 2 carbons, each one of those has 4 valence electrons. I've got 4 hydrogens, and I'm going to put a hydrogen on each one of these, or 2 hydrogens on each one of these. And then I still have these electrons need to be shared. If I share a pair of electrons here, I still don't have an octet, I'm 1 short, so we're going to take these electrons and we're going to share them as well. Okay, again, you'll see what's happened here is that I have 1, 2 sigma bonds here. 1 of these bonds in the double bond is a sigma bond, but the other one is a pi bond that's caused by the overlapping p orbitals. So how can I tell that this oxygen and these carbons are sp2 hybridized? Because they have 3 things around them, 3 items, whether it's bonds or whether it's lone electron pairs. So I have a double bond and 2 lone pairs, 1, 2, 3, okay? Same thing is true with these carbons down here. I have 2 single bonds and a double bond, 1, 2, 3. 3 items mean that I am sp2 hybridized, okay? Finally, sp hybridization is going to form 2 sigma bonds. It is possible for it to form as many as 2 more pi bonds because it's got two p orbitals that it has not hybridized. Best example of this one is C2H2. And so let's get a picture of that one up here. So if I've got C2H2, again, I've got 4 electrons around each one. I'm going to stick a hydrogen here. I'm going to bond these 2 together, but again, in order to have an octet, they're going to have to share that pair and they're going to have to share this pair as well. Okay, so I've got a sigma bond here. One of the bonds in a triple bond is a sigma. The other 2 are pi bonds. All right. How can I tell that this is sp hybridized? Because this carbon atom has got 2 things around it. It's got a single bond and a triple bond, and so that tells me that it's going to be sp hybridized. So really all you're going to have to do is look at the central atom, say, all right, how much stuff is around the atom, and that's going to tell you what the hybridization of that particular atom is.